Okay, students, welcome again. And now we have discussed about how Verilog acts as an HDL. Already we have discussed about Verilog as an HDL, and today's topic is all about the popularity of Verilog. So in this, basically, how this HDL, the popularity, main exaggeration of HDL, what are the things that we can see over in this HDL is all about. First one is concurrency. So what is a concurrency? Concurrency here in HDL is in an electronic circuits, all the units are to be active and functioning concurrently. So here in this, all the modules or else all the electronic circuits, all the devices will be acting concurrently and they function concurrently. Parallelly they function. It's not by one, but they function concurrently, that is parallelly, and they are inactive. So the voltages and currents in different elements in the circuits can change simultaneously. In turn, the logic levels too can change. So as here the concurrency basically means the devices, the electronic devices which are in the active mode, they work concurrently, that is parallelly they work, so that the voltages and currents in different elements in the circuits, they can change simultaneously, parallelly they can change, such that we are saying it is the concurrency, the working of all the electronic devices can be seen parallelly. Concurrency, the concurrency is achieved in this particular Verilog as an HDL. So in turn, the logic levels too can change as we are changing, or else we can see the changes in the voltages and currents, so that we can see the logic levels of that particular electronic device too can be changed. And now, simulation of such circuit in HDL calls for concurrency of operation. So the simulations can be run parallelly, and so that we are calling it as the simulation of such a circuit in HDL calls for concurrency of operation. So when the two devices, for example, when the two modules have to be run parallelly, then the concurrency can be achieved 100%. So here we can change the voltages and the currents simultaneously. Okay, and now the Verilog simulators are built to simulate concurrency. So here the simulators in this particular Verilog, they are inbuilt to simulate concurrency. To run the program, each individual modules can be created, can be inbuilt to simulate concurrency. So everything was inbuilt in order to run the program, one or two programs concurrently. This is all about the concurrency. And coming to the synthesis and simulation. So what is this synthesis and what is simulation? So here it says about the design that is specified and entered as described earlier is simulated for functionality and fully debugged. So here in order to simulate the particular program, the synthesis has to be done prior. Synthesis and simulation. Okay, so the design that is specified and the design which is specified and that is entered, which is described as earlier, is simulated for functionality and fully debugged. So without any errors, all this part has been done prior. That is nothing but the synthesis. And after removing the errors, after checking out all the errors in the program, then the simulation process will be done. So the translation of the debugged design into the corresponding hardware circuit using an FPGA and ASIC is called synthesis. So here the word synthesis is talking about the translation of debugged design. So the translations of a particular the translation of a particular code without any errors can be designed into the corresponding hardware circuit. How? Using FPGA or an ASIC. So field programmable gate arrays or else an ASIC is called the synthesis. Translation of debugging the design into corresponding hardware circuit. The debugging of the particular the debugging of the particular program into corresponding hardware circuit, checking out everything is nothing but we calling it as a synthesis. And the circuit realized from them are essential direct translations of functions into the circuit elements. So the circuit which are realized from this synthesis can be are essential direct translations of functions into circuit element. Okay, so then coming to the functional verification, or after synthesis, after simulation, and here go with the verification. Okay, so what is a functional verification? Functional verification is nothing but testing is an essential ingredient of the VLSI design process, as with any hardware circuit. So for any hardware circuit in the HDL, in the Verilog, we have to test. We must test. Why? Because there are some worms will be there in a particular program. So in order to free from that bugs, or in order to free from that free from the worms, we have to test. Okay, so testing is an essential ingredient in the VLSI design process, as with any hardware circuit. So if you take any kind of hardware circuit, we need to there is a process has to be gone through, that is a testing. Okay, we need to verify the code, we need to test before process, we need to test itself. Okay, so it has two dimensions to it. What are those? Functional test and timing test. So there are two tests can be performed in this functional verification. So they are functional test and timing test. So testing or functional verification is carried out by setting up a test bench for the design. So in order to test something, in order to test the module, in order to test a particular hardware circuit, there are two types of tests can be performed. One is functional test and another one is timing test. So in order to test or functional verification is to be carried out, it has to be carried out by setting a test bench for the design. Okay, the test bench setup has to be made in order to verify the code of a particular module. Okay, this is all about functional verification. So till now we have discussed about the concurrency, synthesis, simulation, and the functional verification. And coming to the next one is system tasks. So what is this system tasks? You all know tasks. Task is nothing but a particular job that we have to perform. So what does this system task talks about? So number of system tasks are available in Verilog. As we are discussing about the Verilog as an HDL, in this Verilog, we could see number of system tasks which are available in the Verilog. Coming to this, though used in a design description, they are not part of it. So as we see, we are telling that there are number of system tasks which are available in the Verilog, but though used in a design description, they are not part of it. So they are present in the designing part, but actually you can't see, there is no part of it. That means what? If for a particular module, if you want to design some particular module, you could see some tasks to be performed you could see some tasks to be performed in order to know the particular status of the module. So in that, you can see a design description of the particular module, but you cannot see but that particular the action taking place is not actually part of it. Okay, this is a point to be remember. And next is some task facilitate control and flow of the testing process. So here some tasks which are available in the Verilog, they are facilitated to control. Those particular tasks, they are meant only to control and flow of the testing process. So for each and every system, for each and every task, there are different tasks which are meant in the Verilog. So few tasks, they only concentrate on the control and flow of the testing process. And next, a set of system functions add to the flexibility of test bench. As I said test bench is nothing but see, the functional testing or a functional verification is carried out using test bench in order to verify in order to test some module, we have to set up a test bench. So this test bench, the set of system functions add to the flexibility of the test bench. So as per the flexibility, as per the convenience of the test bench, then only the task can be done, task can be considered in this particular HDL. So there are of 3 categories. So this system task can be carried out within the 3 categories. We have functions that keep track of progress of simulation time. So here we could see the first task, the first system task is the functions that are kept, which are to be, functions that test the process of, keep track of the process of simulation time. The simulation time is the main constraint to be considered in order to perform a certain task. And the second one is function to convert data or values of variables from one format to another format. So the first one is simulation time, the second one is conversion. Simulation time, the second one is conversion. Okay, the conversion of data or variables from one format to the another format. This is another task. This is another category in the system task. And the third one is functions to generate random variables with specific distributions. So here another task, another category that we could see in the system task is the functions of generated random variables, random numbers with specified distributions. So as per the task given, we need to generate the random variables as per the distributions. Okay, so these are the 3 categories that you could see in the system task. And coming to the last point is there are numerous system tasks and functions. As I said you, this Verilog consists of various number of system tasks. So these are the only things that we see. These are the things that we see. But also we can see there are number of numerous system tasks and functions can be available in the Verilog. Okay. Next, coming to the programming language interface. So what is this programming language interface? Programming language interface, it is a way to provide application program interface to Verilog HDL. So this is a programming language interface. You just ponder on the heading saying that programming language interface. This is an interface. What is its interface is? It is a way to provide application program interface. So in order to provide an application to the Verilog HDL, we are going through this programming language interface. That means what? In order to provide the application of particular module, we are using this programming language interface. So essentially it is a mechanism to invoke a C function from a Verilog code. So in order to see, we have Verilog code. So in order to bring out the application purpose, we are saying that it is essentially it is a mechanism. It is a mechanism to invoke C function from a Verilog. That means from a Verilog code, we can easily write, derive a code which with the help of this C functions. Okay. Next, PLI, that is programmable language interface, used for doing the things which would not have been possible otherwise using Verilog syntax. So another way that we could see, we could interface or else we could provide an application programming interface is with the help of Verilog syntax. Okay, other than the C program, we can also invoke using the Verilog syntax. This Verilog syntax has consist of modules. Yesterday we have discussed in the last class, that is saying that in the module you have a module saying the syntax starts with a module and you have few statements and end with the end module. Okay, so this is a basic syntax, Verilog syntax, in order to write a particular code for a particular electronic device or else a module. Okay, so the key functions of the interface are as follows. These are the key functions for the interfacing the programmable languages. They are: one can read data from a file and pass to Verilog module as input. Such data can be test vectors or other input data to the module. So here the first and the foremost thing that you have to remember is one can read data from a file and pass to the Verilog module as input. So for suppose if this is a Verilog module, you can read data from a file. If this is a file, you can read data from a file and you can pass this file into a Verilog module as a input. Okay, so you can read data from a file and you can pass it on to the Verilog module as an input. So such data can be test vectors and other input data to the module. So here this data can be a test vectors or input data to the module. Obviously, when you are giving some information from the file to the input to the module, it's acts as an input. It is an input, just it's an input. So that input could be of a test vector or else other input data to the module. Next, similarly, variables in Verilog modules can be accessed and their values written to output devices. So here the second point is variables in the Verilog modules. In the Verilog modules, you have different types of variables that we represent. Sometimes we represent with A or B, sometimes we represent with X or Y, sometimes we represent with clock, clock, and also these are the few variables that we represent. So variables in Verilog modules can be accessed and their values written to output devices. So at the output, if this is the input, at the output we can easily see the Verilog modules can be accessed and their values written to output devices. So whatever the values the Verilog, after verification, after synthesis, after simulation, synthesis, simulation, and after verification of the code, whatever the output that you are obtaining, that can be carried out or else can be seen at the output. Next, delay values, logic values, etc. within a module can be accessed and altered. So here in this, within the module, for suppose within the module, you can change, you can alter the delay values or logic values. Delay values is meant with the timing. Okay, with proper timings, the values can be reading out or not. So these are the delay values. If the data is being delayed, for how much of time the data is delayed. Okay, so all these values and logic values within a module can be accessed and altered. That means what we can change, we can access and we can change as per our convenience. Next, blocks written in C language can be linked to Verilog module. So as I said you here in this Verilog, this is for this programming interfacing, for this particular interfacing, we can see the invoke of C function from a Verilog code. That means what? The C language can be linked to Verilog modules. So the blocks which are written in the module in C language, they can be linked to the Verilog modules. Coming to the module concept. So what is this module concept? So the module concept is any Verilog program begins with a keyword called module. So this is one of the most important topic to be remembered, and also it is a very essential in order to write a program in a HDL. So in order to write a program in HDL, first thing you have to know what is a module. So what is a module here? Any Verilog program begins with a keyword. It is a keyword. Okay, module is a keyword. In order to write any program in the Verilog, it is essential to write or start with a keyword saying a module. Okay, next is a module is the name given to any system considering it as a black box with input output terminal shown in the figure. So in this particular figure, if you observe, this module is a name given to any system, any kind of system, or else, for example, if you want to write a code for a multiplexer or else encoder. So what is this? You have to write mentioning with a name module. Okay, so the module is a name given to any system. So the module, I am giving the name to a multiplexer as module mux. Okay, so the system considering as a black box. So this module consists of, this multiplexer consists of some particular input and it consists of some particular output. So terminals, input and output terminals. So a module is a name given to a particular system considering what inputs and as well as the outputs. So the terminals of modules are referred to as ports. So the input terminals and the output terminals for this particular multiplexer module, my input terminals are input and output terminals are output. So I am telling that input and output terminals are nothing but the ports. So if something giving as input to the multiplexer, then it is called as the input port, and something which is coming out of the multiplexer, it is nothing but the output port. So the terminals of the modules, you have to remember, terminals of the modules are referred to as ports. So coming to the figure here, if you observe, this is a representation of module as black box with its port. As I said, input and output, we are referring it as a ports, input ports and output ports. For example, if you say this is a module, okay, for this module you have input ports and you have input ports and output ports. Okay, so the input ports and output ports, for example, here you see the input ports are you have input port, output port and in-out port. Okay, so what is this? Module adder. For example, if this is an adder, the module or else the digital circuits that you are considering it is an adder, then the input ports are X and Y. The input ports are X and Y, and the output ports are A and B, and the input and output ports are P and Q. So the overall, this module consisting of, the module name is an adder. As I said the keyword Verilog program, it should begin with a keyword called module. So this is a keyword module, and my circuit which I am considering is an adder. You can go for the multiplexer, encoder, whatever it is. Okay, but here in this particular figure, I am considering it as an adder. So module, adder, my output ports are A, B, my input ports are X, Y, and also I have in-out ports. Okay, these are the in-out ports as P, Q. So this is how you will represent the module. Okay, coming to the in-depth, we discuss what is a module actually. So the ports attached to a module can be of three types. So the ports which are attached, the ports, for example, if this is a module, you have input ports, you have output ports. So as I said the ports which are attached to the module can be of three types. The first one is input ports through which one gets entry into the module. These are the input ports. Input ports are nothing but these are the ports which one gets enter into the module, the name which you are giving, input ports into the module. They signify the input signal terminals of the module. As the name indicates, these are the input ports. They signifies the input signal. Okay, input signal terminals of the particular module. Coming to the second one is output ports. So what is this output port? Output ports are, in the previous example, my output ports are A and B, isn't it? My input ports are A and B. So the input ports are X and Y. In the previous example, we have discussed the input ports are X and Y, and the output ports are A and B. So the output ports through which one exit the module. So input ports are one enters into the module, whereas output ports are one exit. This is enter into the module, and this is exit out of the module. So they signifies the output signal terminal of the particular module. Okay, input module is enter into the module, whereas the variables which are coming out of the module module is nothing but the exit of the module are nothing but the output ports. And in the previous example, in the previous figure, we have discussed input ports are X and Y, and the output ports are A and B. Okay, so the third one is in-out ports. What is this in-out ports? In-out ports, these represent ports through which one gets entry into the module or exit the module. So these are in and out. These are in and out. That means one which enter into the module and one which exit out of the module. So these are terminals through which signals are input to the module sometimes. At some other time, signals are output from the module through this. So here this name clearly indicates in and out. So these are sometimes the signals into the module, whereas the signals out of the module. Signals into the module, signals out of the module. So so that we are calling it as in-output. Thus, one module may not have any port at all. Thus, one module may not have any port at all. Another may have only input ports, while a third may have only output ports, and so on. So here in this particular sentence is talking about the module may not have all the input ports all time. Okay, all the input ports, all the output ports, or else all the in-out ports one time. Sometimes they may have only input port, some other time will have output port, and likewise, and so on. Okay, and all the constructs in Verilog are centered on a module. So all the constructs that you are considering, all the variables, all the constructs will be centered on the module. They define ways of building up, accessing, and using modules. All the constructs which you are considering for a particular module, they are centered already in the module, and also they define, the constructs will define us the construct will define us to build up, to access, okay, and to use modules. So a module comprises a number of lexical tokens arranged according to some predefined order. The possible lexical tokens are of 7 categories. So as I said you, the constructs which are present in the Verilog, they are centered on the module, and these modules are comprised of few tokens. Okay, these tokens are predefined. Okay, they are in the predefined order, and these tokens are of seven categories. This is important points to be remember. What is that? First thing is, all the constructs in the Verilog are centered on the module, and the second one is they are defined, they are considered, or else they are defined to build up, to access, and to use the modules. And the third one is a module which is comprised of a number of lexical tokens, and they are arranged in the predefined manner, predefined order. And the possible tokens, the main possible tokens tokens are of 7 categories. First one is white space, and the second one is commands, third one is operators, fourth one is numbers, fifth one is strings, sixth one is identifiers, and the seventh one is keywords. So these are the main main tokens. Okay, main tokens of 7 categories. They are used to build up. Okay, they can be accessed, and they can used in the modules. Okay. Okay, so this is the structure of a typical simulation module. So in this, in Verilog, any program which forms a design description is a module. As I said you, any program in the Verilog, it must starts with a keyword called module. So in any Verilog program, the design descriptions is a module, and this module used to simulation has a form. So in order to simulate a particular module, in order to synthesize, simulation, verify, it has to be in some form. Okay, so that form is this structure. This is a figure structure of a typical simulation module. So here you see a module test. Here you see some sentences 1 and 2, and you are ending up with this program with the end module. As I said, you module is a keyword. And test is a particular digital circuit. Okay, it's a hardware circuit, digital circuits. In the previous example, I've discussed a figure with a module adder, isn't it? Module adder consists of input port XY, output port A and B, and in-out ports P and Q. Input ports, and this is output ports, and this is in-out port, isn't it? So this is a keyword module, and this is a digital circuit. So in the same way, if we observe, this is a structure for typical simulation model. For this typical simulation model, we have a module test. Test module signifies declaration of the module. This is how we declare the keyword module. And test is name assigned to the module. In the previous example, the name which I have assigned is adder. Okay, here the name I can assign here the adder, multiplexer, encoder, okay, whatever it is. So here my module signifies the declaration of the module, and test signifies name assigned to the module. And the statements in this particular program, we have the some statements to be mentioned. So okay, remember here, after module, keyword, name of the module, and the semicolon. Semicolon signifies the termination of the module sentences, module statement. So after each module statement, we have to end up that particular statement with semicolon. It is important and foremost thing to remember, semicolon, giving a semicolon. Next, coming to the statements. These statements are nothing but individual statements within the module. So for each module, you have some statements to be mentioned. Okay, as I said, you can go. This is a invoke of C program, so you can go for this statements could be of this statement could be consist of else if statements, loop statements, do while. Okay, like that. Next, coming to the end module. End module is, it signifies a termination of a module. So when you are starting a program with a module name, and you have to end up that module with the end module. Okay, this is the end module. So this is about the structure. This is a structure of a typical simulation module. Next, we have a module syntax. Some syntax has to be followed for each and every module. Okay, so for this module syntax, you have module underscore name, that is name of the module. In the previous example, I have considered adder, and I have considered multiplexer. Okay, multiplexer, like that. So module name, module name, and port list. Port list consists of input port, output port, and input output port, like that. Okay, port list. Next, input output in-out declaration. Next, intermediate variable declaration. So input output in-out declaration, we have to declare what are the input ports, what are the output ports, what are the in-out declaration. Okay, and next is intermediate variable. Some variables, if you are declaring, you have to declare in the immediate next to the port list. You have to declare the intermediate variables, if any variables that you are considering. Next, functional description. So what kind of function are you describing about the particular module? So the functional description has to be mentioned. For example, the functional description is nothing but, for example, gate. If you are considering the module name would be of AND gate, or here module name can be given as AND, or like that, AND gates. Functions and switch. Okay, sometimes transistor will act as a switch. So transistor, what kind of transistor? What kind of transistor is a module name? So the functional description about that transistor, and data flow and the behavioral flow. Gate, switch, data flow, and behavioral flow. These are the functional descriptions of a particular module. In the previous class, we have discussed what is gate level module. Okay, what is switch level module? Switch level is another name for switch level is circuit level. Okay, circuit level. And the data flow. Data can be transferred from one register to another register easily without any interruption. And the behavior model. In the behavior model, this is one of the important level where in this behavior model we have discussed many things. Okay, so these are the functional description. In the syntax you have to mention. And next is, as we have started with the module name, we must end with the end module. Okay. Next, simulation and synthesis tools. So a variety of software tools related to VLSI design available. So basically there are two types which are available is model sim and spectrum or mentor graphics. Model sim or mentor graphics, these are the two foremost software tools which are related to the VLSI design, and model sim has been used to simulate the designs. Okay, in order to simulate the designs of a module, we are going for this model sim software, and Leonardo spectrum or else the mentor graphics, Leonardo spectrum of mentor graphic has been used to obtain the synthesized circuits. So for the simulation, to simulate the design part, we are going for the model sim, and also to synthesize circuits, we are going for this mentor graphics, Leonardo spectrum of mentor graphics. So these are the two software tools which are related with this VLSI in order to perform a particular program related to the different digital circuits. And test bench circuit syntax. Test bench syntax is a test bench is a HDL code. It is an HDL code that allows you to provide a documented repeatable set of stimuli. So in this test bench particularly, it provides a documents. Okay, it provides a documents which are repeatable set of stimulates. You could see some repeatable set of the things which are the concurrency, the redundancy. The redundancy can be seen in this test bench. So the test bench syntax is module test bench module name, same like a normal module syntax. In this test bench syntax, you are representing test bench module underscore name, in out input or declaration, same like the previous one, module syntax, and the intermediate variable declaration, same. And here coming to the test bench signal, here you will see the stimulus. Stimulus means initial or always. These are repeatable. Okay, we can repeat the set of stimuli. We can repeat the initials. We can repeat the always, and we are ending with the end module. Okay, this is only exclusively for the test bench sector. You could see the differences between simulation and synthesis too. You can see the differences between the module syntax and the test bench syntax. In the test bench syntax, here in the module syntax, you see the functional description, whereas in the test bench syntax, you see the stimulus. Okay, the repeatable set of stimuli, that is initial or always, can be mentioned in this test bench syntax, and you have to end up this syntax with end module. Why? Because as you have started with the keyword module, you must end up with the end module. So dear students, this is all about the module concept, the concurrency, and the simulation and synthesis, and the syntaxes, different syntaxes. One is test bench syntax and module syntax, and software tools. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.